Continuing on with Bellman's equations. So just like we defined the value of a state, we also have state action value. So given a state and an action, you can also assign a value to it, which tells you how good it is to take that particular action from that particular state. So we begin with the usual expression. So this is the expression for the discounted total reward. RSA is equal to immediate reward plus discounted expected future reward when the transition is from state S to the new state S prime here. Now, this action A, if you see here, we are looking for how good it is for a given state and a given action, and that is the value. So we have to find how valuable it is to take each action from a given state. Therefore, we are not looking, we'll just ignore the policy here because we are looking at every possible action. What is the value of taking action A? What's the value of taking action B? What's the the value of taking action C, and so forth. So we will temporarily discard the policy here. However, that's only for this particular state, and then subsequently we will adopt this policy, the given policy. So here, only for evaluating from state S all possible actions, we will have to evaluate all possible actions, but the pi gives you one particular action, the policy gives you one particular action. So how are we going to evaluate all possible actions for state A? Therefore, only here we shall discard the policy, and thereafter we shall continue with the policy. So this is the immediate reward when taking action A, and this second term here is the discounted expected future rewards under policy pi. And that is the Q value. So the Q value given a policy pi is the how valuable is it to take action, any action A from state S when following policy pi, and that policy pi will be followed for the remainder of the episodic thing that the agent is interacting with, except for here, immediate reward. And for each possible action A, the transition probabilities will also change. So that RSA is the same thing as the Q value of SA under policy pi. And subsequently, our S prime pi S prime is Q pi S prime pi S prime. Here, the action is based on policy pi. Now, we can rewrite this as, because this Q pi S prime pi S prime is when you are following the policy. So that is the same thing as the value of state S prime. So this is the formal definition of the state action value, or simply the Q value. The state action value, or simply Q value, for any given state and action A under a policy pi is the immediate reward when taking action A in state S and following policy pi thereafter. So this is the Bellman's equation for state action value or Q value. Q pi SA is equal to RSA plus gamma, the discount, times expected. So summation P of SA S prime for all values of S prime, Q pi S prime, pi S prime. And since this is just a function of S prime, when following this action now is not any arbitrary action like in here. Here we have to evaluate the Q pi for all possible actions. And here this is the action given the policy pi, and so this can be replaced with V pi S prime, giving rise to this expression here. So here are the Bellman's equations using state values. Q pi SA equals RSA plus gamma times expected value of the next state, or it's equal to the immediate reward plus discounted expected value of the Q value of the next state when following the policy pi. Now this is something that you should also remember. That's V pi S is equal to Q pi S pi of S. The action, when you're following the policy pi, then you don't have to evaluate the Q for different actions. So that's the same thing as the value of the state. Here's a simple example. This is the same example that we did last time. So we have 4 states, P, Q, R, S, and we have 3 actions A, B, C. We have the discount gamma, and these are the 3 tables are the transition probabilities for this is current state and this is the next state, the same for the other tables. The difference is this is when the action is A, this is when the action is B, and this is when the action is C. And these are the corresponding rewards when you're taking from state P, Q, R, and S actions A, B, and C. These are the rewards. And the policy is here, but since we are looking at the action for all possible values of the action, we are looking at the Q values for all possible values of the action, excuse me. So we ignore the policy for now. So our goal here is to find the Q values when we are in state P and for all possible actions A, B, and C. And we shall denote them as X, Y, and Z. So X, Y, and Z are the Q values corresponding to actions A, B, and C when we are in the state P. And so I will be using this expression here because we already have in the previous set of lectures, we already found out the value of each state, P, Q, R, and S. So we know those values, and now we shall be using them to find the Q values. Okay, so what I shall be doing is, before I use this Bellman's equation, I shall fill out this table because I'll need the probabilities for all possible actions A and state S prime. Next state is S prime here, which is P, Q, R, and S. And this action A is a generic action here. It's not this specific action A here. So this is a slight misuse of notation. I hope it's clear to you. So the first goal is to fill out these tables. These tables, this table will give us all the transition probabilities when you're in state P and for the three actions A, B, and C. And again, from state P, the rewards will be stored in this vector here. Okay, so this is the tables that we have. And now, since we are looking for actions from state P, so that's our state here, and our first action is A. So for action A, we shall be referring to this table here, the first table, because that corresponds to action A, and the state is P. And so this is the set of transition probabilities to P, Q, R, and S being the next state. And the reward from state P when taking action A is 0. So we record this. So using Bellman's equation, X, which is Q pi PA, is given by RPA, which is the 0 here, plus gamma times 0.9 times value of P plus 0.1 times value of Q. Now again we are on state P. Now let's consider action B. So since we are looking at action B, we shall use the second table here, and action B and from state P, so again the first row, and the probabilities are 0.6, 0.4, and the reward is when you are in state P and taking action B, the reward is again 0, and so that allows us to fill the second row of these tables. And again, using Bellman's equation here, the Q value of action B in state P is Y, which is this 0 here times 0.6 value of Q plus 0.4 value of S. So now again from action P, from state P and action C. So we look at this table here, the third table, which corresponds to action C. And the first row is the transition probabilities from state P, which is 0, 1, 0, 0. And the reward is 3. So we fill the last row of the tables. And then using Bellman's equation, we get this expression here. This is the reward, which is 3, and this is, well, the transition probability. We don't have any summations here because it's deterministic. It definitely moves to Q. So gamma times value of state Q. And so now, since we assume that we know that P, Q, R, S are the values of the state uppercase P, uppercase Q, uppercase R, and uppercase S, we simply plug in those known quantities and we get the values, or rather the Q values corresponding to actions A, B, and C, which are X, Y, and Z. Now, we can now proceed to find the Q values of the three actions from the state Q. I'll pause and let's treat this as an exercise. So this is what we have. This is the two tables, the probabilities and the rewards. And these are the expressions that we get. The end.